So currently we're in section 7 of chapter 5, and it's about applications of Newton's laws. And in this problem here, you have seen two objects. So this is called practice question 5.7.8. And you have seen two objects that are connected by a string or by a cord like this. So last time we have considered the free body diagram. And you know that there are, on M1, there are three forces, right? And so here, and tension, and this is the M1G, and this is the normal force N1. And here you have the tension up, and also M2G down, and we suggested that you chose the coordinate system like this. Since your acceleration is here, so we suggested that your x coordinate, right, choose it to be here for M1, x and y. For M2, we suggested that you chose your new x to be down and your new y to be here. Okay? And very soon we'll see the reason why we did so. And therefore, we can write down for M1, we have the equations, which is sum over fx equals mass times acceleration, and sum over fy equals 0. But for M2, we only have one equation, okay, which is the sum over fx equals m times the acceleration. But this m was m1, and this was m2, right? And now let's write down the equations. So for the equations for m1, we have the equation which is called tension equals the m1 times the acceleration. That's called equation 1. And then for M1, the vertical direction, we have normal force N1 minus M1G equals 0. And that's called equation 2. And then for M2, there's only one equation. And if you call the downward to be positive for M2, okay, there's a reason we did that. But then M2G minus the tension equals M2 times the acceleration. Right? So pay attention, for M2, downward is positive. And if downward is positive, then acceleration is positive, right? Because you know that acceleration here, this downward, this means the acceleration. We make the x prime follows the direction of acceleration so that you don't need to worry about the sign of A. Sign of A would be positive. If you if you align your coordinate positive x to the downward direction, and then how would you solve for A? You can consider equation 1 and 3. Consider 1 plus 3. And if you consider 1 plus 3, what do you get? You'll get t will cancel each other, right? So you have m2g equals m1 plus m2 times the acceleration. So therefore, what's acceleration? Acceleration equals m2g over m1 plus m2, right? And this one, we can call that equation 4. You have obtain the acceleration, then how would you move on? Once you obtain the acceleration, how would you get the tension? Any idea? Mathematically, once you have obtained acceleration, then how would you obtain tension from here? Yes, so you substitute 4 into 1. Okay, so that's great. Let's say equation 4 into equation 1, then you will get this tension should be equal to m1 times m2 times g over m1 plus m2. So that will be your tension. Hey, so let's call this equation 5 here. So then after this, we are done, right? Then you can start to substitute in the numerical values of each quantity, and then numerical value, you know what a g is, right? So then your acceleration should be equal to m1 equals 5, right? So let's look at this page of the size here. m1 equals 5, m2 equals 9. So that will be 9, okay? 9 over 5 plus 9. And this thing multiplied by 9.8, right? And of course, it's a meter per second square, something like this. And you'll get the acceleration in terms of meter per second square, right? So that will be your acceleration. And now what about tension? Tension will be in terms of newtons, right? So the m1 equals 5. So that's 5 times 9 divided by this is 5 plus 9, right? And this whole thing, you need to multiply it by g, right? So now you need to multiply it by g, so then you multiply it by 9.8, right? And meter per second square. And overall you will get newtons, right? You can check the unit, you will get in terms of newtons. So that's the idea here. So now let me ask you a question, so a couple of questions here. So first, compare M2G with tension. Which one would be larger in magnitude? If you think M2G is larger in magnitude, please raise your hand. M2G is larger in magnitude. How about if you think tension is larger in magnitude, please raise your hand. Tension. No? So do you know what I meant here? There are two forces exerted on M2. Conceptually, before you do the calculation, you need to be aware that which one is larger in magnitude. You will see this in the lab. Probably not very soon, but in a lab this semester, you will see such kind of experiment. And if you think M2G is larger in magnitude, what was your argument? If you think this M2G is larger in magnitude compared to tension, what was your argument for saying that? Yeah, yes, okay. So because acceleration is down, right? Since acceleration is down, if you consider F equals ma for M2, M2G should be larger in magnitude, right? So that's one idea, that's one thing. The other thing is, why is the tension the same in magnitude? Okay? Why is tension the same? So this thing if you consider this, I'm sorry. So if you consider this more rigorously, you say, last time we said that the string is massless, right? And the string is taut, and string is inextendable. So the string is massless, so that tension should be the same in magnitude everywhere on the string. Now let's see why. Okay, so if you have a segment of string like this, suppose I have a segment of string, and I divide those string into pieces. Okay? Pieces here. And suppose if each piece is massive, for example, if it were massive, then you have, let's say, delta M1, okay, delta M2, delta M3. Okay? So, but let's consider each piece to be of the same little mass. So let's just call it delta M. Okay? So those pieces, 1, 2, and 3, then if the string is massive, you need to consider that if you want to accelerate the string, then what you need to do is there must be a net force, right? A net force exerted on each segment of string. So now let's look at this segment here. Right? So if you want to analyze the forces, let's say on one hand there will be one tension here. On the other end there will be another tension here, right? And they shouldn't be the same because F equals ma, right? So suppose this tension, let's call that T1, and this tension, let's call that T2, right? T1 and T2. And T1 and T2 would not be the same in magnitude if the string is massive, because you need to have that, you need to say that T1 minus T2 equals that delta M times A, right? So if the string is massive, tension would be different. Let's say, now let's look at this point here. This delta M here, there will be two tension forces. One is the T2 here, okay? Because suppose this is a point of connection, and this will be T2 to the right, and there will be a T3 to the left. And then again, T2 and T3 shouldn't be the same, because if this delta M is massive, right? Similarly, here you can say that there's a T3 here and T4 here. Right? So that's it. And so that means if the string is massive, if you analyze every segment on the two ends of that each segment, the tension shouldn't be the same. So that's why tension will be different if the string is massive, because F equals ma. But if you assume that string is massless, this part is 0. Right? If the string is massless, then this is 0. Then T1 equals T2. Similar argument, T2 equals T3, T3 equals T4. So everywhere on the string would be you have a uniform tension. Right? So then you may wonder, why did I say T3 here and T3 here? Because in a point of contact, you can apply Newton's third law, right? When two strings, they are two segments of a string, they are attached to each other, then there's a contact force, a pair of contact forces. So this T3 and this T3 are according to Newton's third law, right? Because they should be the same in magnitude. That's at the point of contact in between two string segments. So that's about the whole story here, about the whole story that we have here. But now we are going to consider a different method. So now what we are going to do is we are going to consider that we can mentally straighten out the chord. Mentally straighten out the string or the chord, and then we'll see how to reconsider this problem here. So this is an alternative method. Let's call that method number 2. But this method is only valid when you try to obtain the acceleration. Okay? So you can, if you want to quickly obtain acceleration without going through the 3 equations, then there's a quick way. So now let's try to mentally straighten out the chord like this. So suppose this is my M1 connected together with M2. Now, once you have mentally straightened out the chord, now let's try to draw the free body diagram for each. Okay? So method number 2. So you have, for M1, you have M1G down, right? And you have N1 up. So that's for M1. But for M2, once you mentally straighten out the chord, where's your M2G? Now, once you straighten out the chord, M2G will be horizontal like this. Right? But where's your tension? Tension will become this and this. Right? So now here you have tension, here you have tension here. All right? So now, why did I do this? I want to consider 2 objects as motion in one dimension. So that means I want to consider both objects as in one system. So now I extended my system to be here. Okay? So now I consider this to be my system. If I consider this to be my system, then the tension in the string will be internal forces. Internal. Okay? The 2 tensions in the string, now if I consider both as in one system, then those become internal forces. So now, what I need to do is as follows. Just write down one equation. Okay? So let me erase this, okay? Because I do need some space. So this is method 2. Okay? So don't get confused. But if you are satisfied with method 1, you don't need to understand method 2. But method 2 sometimes can be faster. Like in this way, if you want to write down F equals ma, now once you have straightened out the chord, you need to rotate this coordinate backward, right? Rotate in a counterclockwise direction. And so now you only have one coordinate here, which is x to the right and y up. Okay? So once you have this coordinate here, you'll see that write down F equals ma. Now you only have one equation. What is that equation? So now your m is the total mass of the system. So now what's the net force in the x direction? This one, right? In the y direction, we know that these 2 still cancel each other, so no need to worry about that. But in the x direction, now if you want to write down F equals ma for the whole system, what would you write down? You write down M2G as the net force equals the total mass of the system, which is M1 plus M2 times A. Then what is A? A equals M2G, M1 plus M2. Right? Now you can see that compare this equation to this one. Are they just the same? Yes, right? But it's faster because now you only need one equation and you get the answer. So now you can interpret what this means. In this equation, you see that this point here, this part of the equation means the net external force. Okay? Net external force on the system. On the system here, now the system becomes 1 and 2, right? And this will be the total mass. Total mass of the system, right? So basically, this is a restate of like a statement, a new statement about F equals ma. But now you treat these 2 as in one system. So that's our takeaway message here, right? So basically, this answer just tells you F equals ma. If you treat both things as in one system, but you do not see clearly unless you have this kind of picture in mind, right? So that's the way that we can suggest. But actually, if you want to get tension, you cannot use this method. Because if you use this method, tensions become internal, then you will not be able to proceed, right? So you cannot get tension from this method. But once you get acceleration, you can come back to the first method and get tension in this way, right? Because once you have gotten acceleration, then you can say that come back to this method and isolate this system, and then you will be able to get tension, because tension should be equal to m1 times A, right? Tension equals m1 times A if you treat these two as two separate systems. So that's the full story about this problem here. And it's in the homework, right? Homework set 3, right? Homework set 2 will be due this Thursday, right? Homework set 3, and you can, if you finish homework set 2, you can move on to homework set 3. So this will be a classic problem here. Right? But so far, we haven't discussed about friction yet. But, okay, so we'll move on to discuss about friction very soon. Right? So now let's move on to here. So now let's look at the next problem here. Next problem here, you have two objects, and one applied force is pushing that object. That problem actually is in the textbook. But I call it a practice question because I don't want to show you the textbook solution, right? Because we want to solve it from scratch. So I don't want to display the solution. So I call it a practice question here, but actually it was from a textbook here, right? So now how would you solve this problem here? Right? So think about this one, right? So let me address the question here. So there are two blocks. Suppose you know the masses. Right? Unfortunately, they didn't give you any value, but they assume that it's a symbolic question. So first, find the expression for the magnitude of the acceleration of the system. System means the m1 and m2 together. That means the system. Part B, determine the magnitude of the contact force between the two blocks. Right? So this question looks simple, but part B is actually not very simple. And you need to think about this for a while. Right? So now let's move on. Right? So, oh, by the way, before I erase this one, so if I ask you this acceleration, the previous question, when if I ask you whether this acceleration A is greater than G or equal to G or less than G, how would you answer that question? So here, we have equation 4 here, right? We have equation 4 here. You can compute acceleration, but this number, will it be greater than G or less than G or equal to G? Will be less than G, right? So I think it's obvious because that acceleration equals, if you consider acceleration over G, you'll get a ratio like this one, right? M2 over M1 plus M2. And this ratio apparently is less than 1, right? Therefore, you argue that A will be less than G. So the purpose of such a machine, consider that as a simple machine, it will give you a horizontal constant acceleration on M1, right? But the drawback is that acceleration will never be larger than G. It will always be smaller than G, like this, because of this answer here. Okay? Let me say again. The purpose of that machine in the previous problem is called a simple machine. Simple machine, we want to use that machine to achieve motion with a constant magnitude of acceleration, say for M1 here, and without the help of your hand, right? You don't need to pull it, because if you pull it, it will not be a constant acceleration. But then the drawback is that constant acceleration is less than G. But if you tune the masses, then you will be able to tune that acceleration, right? So now let's move on to the next. This problem here, how would you solve this problem? Okay, so now I'm going to erase the whiteboard. Okay, sorry. So let's erase this. Yeah, next time I should bring cleaner here, like a liquid cleaner. Now this board becomes hard to erase at this point. So make sure you start working on homework 3. Okay? There are also quite many questions in homework 3 here. And of course, there will be a homework 4 before the second exam. Right? But at some point, like sometime later this week, I will post homework 4. So our lecture progress, we are not fast. You know that we are not fast, right? But now let's move on here. So from here, we can write down an equation. But now let's consider part A and part B of a question. Let's call this practice question 5.7 point B. And there are 2 parts. So part A of a question, you find the magnitude of acceleration of the whole system. So since they want you to define everything as one system, so now you need a free body diagram. You need a free body diagram here. If you treat both M1 and M2 as in one system, so now suppose you have M1, right? You have M2, and just consider them as in one system. Right? Just the whole thing. The whole thing, consider them in one system. Then the total mass will be M1 plus M2, right? Then can you apply F equals ma to such a problem here? Yes, just treat them as a point. Okay? Just consider, don't worry about the volume of the 2 masses. Just treat them as one single point in one system. So then, if you treat them as in one system, for example, you encircle them, right? Encircle them as in one system, and there's a net force F acting on the system, right? You can consider that in this way. So then, how would you write down F equals ma? Should be straightforward, right? So that F will be equal to the total mass m1 plus m2 times acceleration. But you may wonder, what about normal force, right? What about gravity? If you treat them as in one system, what you consider is as follows. The normal force will be, there's the overall normal force here, right? But the gravity will be the gravity from the whole system. So that means consider M1 and M2, they are attached together just like a single mass. So then that will be, gravity will just be equal to M1 plus M2 times G. Right? But these two, we believe that should cancel each other because the whole system doesn't have any tendency to move in the vertical direction, right? So that means the vertical part, you should have normal force minus M1 plus M2 G equals 0. Again, this normal force is the total. We can consider that as the N total, right? The total normal force, this is the N total here. But that's, second equation is not our purpose, but the first one is. So from the first one, you can obtain acceleration. What is acceleration? If you know this, then acceleration should just be equal to the force over the total mass. But here, you don't see any number, right? But if you start working on the homework, you will see some numbers. Then you can practice those numerical values, right? Part A of the question. Let's look at part B. Now, they wonder what's the forces in between the 2 blocks. So remember, when we treat these two as in one system, the contact forces between the 2 blocks, we don't take them into account because those are internal forces, right? There are also like forces in between, like among the molecules within each block. We also don't consider those forces. Those are internal forces. F equals ma, you only consider external forces on one side of the equation, right? These are external forces. If you read the textbook, those are external forces, right? So now let's move on to consider the next. Let's consider the next, which is get the contact forces between them. So now let's consider 2 separate free body diagrams. So now you have M1. What are the forces exerted on M1? So let me name some forces. Let's say M1G. Right? And there's a normal force, N1. Right? So those are the 2 forces that we have. Now, let's move on to consider another mass. But it's not complete. Okay? It's not complete because I'm going to show you other things. But now let's look at M2. For M2, what are the forces on it? Right? So for M, let's say this is M2. Yes, okay. Let's call this M2 here, and there will be M2G, and there will be N2 here, right? And these two should cancel out each other. But now, what else? Do we miss anything? We assume no friction. Okay, so far there's no friction here. Now we wonder what's the interaction between them, right? So what's the direction of interaction between them? So the next thing is, for M1, there's a force pushing M1 here, right? So now we are considering the force pushing M1 here. Let's call that F, right? That's the F which is known. But now, do we miss anything? There's a force pushing M1. So on M1 and on M2, we miss something. So what are those things we miss? Yes. Okay. So that's great. We miss the contact forces between them. So now let's be careful and think about the direction. From your real life experience, when two objects they push against each other, right? So those forces will arise in pair. Actually, according to Newton's third law, right? So we talked about Newton's third law in the previous lecture. They will push against each other. So there will be one force here, and the other force here. They push against each other, right? So this force, we can name it, we can call this P, and that P means push, okay? So our textbook notation, that P means push. We call this P 2 on 1. And this force, we call it P 1 on 2, right? P 2 on 1 and P 1 on 2, they are both vectors, but they are the same in magnitude, opposite in direction. They always act along the same line, and they do not cancel each other if you treat them as two separate objects, right? So is that clear? This P 2 on 1 and P 1 on 2, those are a pair of forces. They will arise simultaneously against each other. They act on different objects, so that's why when you treat them as two separate systems, they do not cancel out each other. Okay? So are we complete in terms of all the forces? Hopefully. Hopefully we're complete in terms of all the forces. So now let's try to solve the problem. Try to solve the problem here. So usually when I solve a problem that involves concepts, I will slow down. Okay? But otherwise, we can speed up. Like after this problem, we can speed up to when we solve other problems there. So this problem is actually very important. When you work on the homework, you will see 3 blocks, right? 3 blocks, and they are moving in the same system, and then you are going to consider some forces as well, right? But now how do you write down the equations for M1? So you look at that. So for M1 here, what should you write down? So let's focus on the x direction. Okay, x direction, you have the equation. X direction, you have the F minus P. Okay, P 2 on 1. Okay, so let's say P 2 on 1. In the textbook, they just call it P 21. Okay, but here I inserted the proposition so that could be clearer. So F minus P 2 on 1 equals the mass of M1 times the acceleration. So pay attention. These two things, they should possess the same magnitude of acceleration, right? Because they are moving together actually, right? There's no gap between the two objects. So one equation, you got this one. And vertical equations, I don't write it down, okay? Because when I know that it's not going to be useful. You have vertical equation, you have this n1 minus m1 g equals 0, okay? I wrote it down here so that you don't get So vertical equation, there's a n2 minus m2 g equals 0, okay? But these two equations are not useful if there's no friction, right? If there's no friction, these two equations are not going to be used, so I put them there. So F equals ma. Horizontally, you get F minus P2 on 1 equals M1A. And for M2, you have another equation, right? This is M. For M2, you have an equation called P1 on 2 equals M2A, right? So the second equation is P, okay? 1 on 2 equals M2A, right? So now, how do we proceed? Since we know A from the first part of the problem, so this problem is not so clear. Assume that we know force. We know the two masses, but we don't know anything else. So part A, you got acceleration, right? So this part A, you can call that equation 1. Equation 1. And now you have other equations, 2 and 3. So how would you solve for the forces? You know that according to Newton's third law, you are confident that the P will be the same in magnitude both, right? But now you can verify. You can substitute that A into here, you get the expression for P2 on 1. You substitute the A into here, you get the expression for P1 on 2. Let's try it, okay? Let's try to say, how would you get P1, 2? Say P1 on 2 should be equal to M2 times A, right? M2 times the acceleration. Acceleration is that. So acceleration is F over M1 plus M2. So P1, 1, 2 will be this thing, M2, M1 plus M2 times F. Will just be a fraction of F. You can see that P1, 2 or P1 on 2, this ratio is less than 1, right? So that's why if you compare P1, 2 and the applied force, which one is larger? Applied force will be larger, right? Will be larger, and here you have a fraction, so that's why P1, 2 will be smaller than F. Let's try to verify what is P2, 1. Okay? You substitute A into this equation. So this one, you substitute equation 1 into equation 3. Right? So equation 1 into 3, you get this result. So now let's just try to consider the following. Let me erase this, okay? Because I need some space. But currently, we're in part B of a problem. Yeah, today, there are fewer people, I think, because of the job fair. Okay? But actually, it's very important to attend lectures. Today is the job fair, so. But it's great that you are here, okay? So because it's very important, we talk about these things. So now let's look at at P2 on 1. Okay, how would you get this one? So P2 on 1, let's call it P2 1, should be equal to F minus M1A. Do you see that? So I shift this to the left and shift this to the right, and then flip both sides of the equation, you will see this. So now let's try to substitute A. So okay, substitute 1 into 2. Okay, equation 1 into equation 2, then you will get this thing. Now you will get F minus, and let's write down F. F minus M1 times A. But A is that, right? Minus M1 and M1 over M1 plus M2, then times F. Right? M1 times A is this one. And then you can see that what is this stuff here. This stuff means here you have 1 minus M1 plus M2 times F. Okay? I extract the common F here outside of the bracket. Then you can play with the algebra. Right? Then you will see that this thing will just give you M2 over M1 plus M2 times F. And it will just be exactly the same answer as here. So now we have shown you that, we have proven that P2 on 1 or P2 1 magnitude should be equal to P1 2 magnitude. Okay? P1 on 2 magnitude. Yeah. So sometimes you can insert the proposition on so to help you understand. But once you have understood it, you can remove the on. So that, like our textbook, they don't show that on here, right? But that can also be a bit confusing if you don't see that on here. That can also be a bit confusing. But we have finished the story. Okay? This problem we finished in entirety, and we also verify Newton's third law, right? We have verified that the two forces they should always be the same in magnitude, and here we assume opposite in direction, and we got the correct answer, right? So that's it. So although this looks simple, but when you start to solve homework problem, can also be a bit confusing and definitely will be relevant to the next exam as well, right? Okay, so now let's look at this problem here. This problem It's can be quite interesting here. It's not from our book, but it's somehow relevant to the homework. Okay, not a textbook example, but if you look at the homework, there's something similar to this problem here. So now we want to consider this wedge here. Okay, so a wedge here, and there are a system of two masses, and we wonder what's the following. Want to get the first, okay, part B of the question, magnitude of the acceleration, and also find the tension in the core. Right? So this is another simple machine. Another simple machine, because in the previous one, we have one mass moves horizontally, right? The other mass move vertically. But now, let's look at this new simple machine here. I'm going to erase the whiteboard, and we are going to start soon. Right? And again, those slides are also on Blackboard already early on, right? So we put those slides on Blackboard already, so you can refer to those slides. So it's in a file called Practice Question for Section 5.7, right? And those questions are actually quite important. So this chapter 5 is actually the foundation of physics 1. Right? The foundation of physics 1, that means everything we talk about in chapter 5 are quite essential for your learning for the later chapters. So you need to really understand chapter 5 very well, right? But otherwise, the foundation would not be solid. Right? And if you are in mechanical engineering, if you are going to take statics and dynamics in the future, and of course, this chapter 5 and also other chapters, later chapters are all relevant to your advanced courses. Yeah, it's hard to erase, I'm sorry. So let's think about how to solve this problem. This problem, when you solve for the first time, is not easy. Okay? This problem is not easy for the first time. Okay, so now let's move on from here. Sorry, I have a lot of things. Try to move on quickly, okay? Because we have only a limited amount of time. And this problem here, let's consider free body diagram first. Here, like this, right? And this angle, let's make it general. Let's call it theta 1 here. This angle, let's call it theta 2 here. And we want to decompose the forces. But now, we also want to set up our coordinate system, right? So here and here. And there's a wedge like this. And you have two blocks, right? And block of mass M1 and block of mass M2. So now, let me ask you, for this problem, if you simply make a judgment regarding the numerical values you have seen here, what will the direction of acceleration be? They ask about only the magnitude of acceleration, because the direction of acceleration are different for M1 and M2 respectively. So in this case, we'll simply try to make a judgment regarding the direction of acceleration. What would that be? Okay, so this is something you should think about, right? But we'll let's say that we don't make a judgment right now, okay? Because from the numbers, looks kind of confusing. Because here you have 100 kilogram on the left, right? That's heavier. But the angle of inclination is smaller on the left, right? So it's kind of confusing. But on the right, you have a lighter weight, right? A lighter, smaller mass. But you have a higher value of the angle of inclination on the right. So it was kind of confusing, right? It's hard to make a judgment how this system will move. So you can make an assumption. But if it's wrong, I mean, it's okay. I mean, because in the math will tell you what's the right direction of acceleration. So now, which direction would you consider? Towards mass 1. So you want this to slide down, right? Okay, so great. Now let's make this assumption. So we assume acceleration is here. Okay, assume. Okay? But if our assumption is not right, it's fine. I mean, the math will correct us. That means when you make a wrong assumption, if you do everything consistently, then you will see a negative acceleration. That means your assumption was wrong, right? So but here, we made such an assumption here. So now, my recommendation again, when you choose your coordinate system, you choose your positive x to follow the direction of acceleration. Let me say that again. That's the best way, okay? Otherwise, now we are not sure what's the direction of acceleration already. So that means we want to be consistent. So call your positive x here, okay? So this is your new positive x, okay? Let's call it x prime, okay? And this is your y prime. Let's do this, okay? So is that okay? So choose your positive x to follow the direction of your acceleration for M1. For M2, choose your positive x to follow the direction of acceleration for M2, like this one. Okay? So for this problem, you can see the benefit of such a choice. I call this y double prime, x double prime. So my x double prime follows the direction of my acceleration. So now let's do the free body diagram. Okay? So the rest, we can do it quickly and see if we can achieve the expression. So how would you get the forces on M1? Okay, see how many forces are exerted on M1. So let's do it quickly. Okay, so this is M1G, and this would be a normal force N1, right? So be careful. Now this is your new x. So you should decompose your M1G onto the two directions. So you decompose your M1G onto here and here. And if this is theta 1, this is also theta 1, right? So now let's name each component here. For M1, this component, the horizontal component, is actually, if you look at trigonometry, is actually M1 G sine theta 1, right? This is sine, and this component is cosine, right? This is M1 G cosine theta 1, right? And let me write down somewhere else because I don't want to take our space for other stuff. So this is M1 G, and this is M1 G cosine theta 1, right? Now let's look at this thing here. This thing, there are accelerations like M2G, right? M2G, yeah, this is kind of harder to draw. This is theta 2, so this is your M2G. And M2G, and you decompose it onto the two directions. And here, let me say again, we assume acceleration to be here, right? And then this will be your normal force, N2. N2, okay? So then this component is called M2G sine theta 2, and this component here is called M2G cosine theta 2. Because if this is theta 2, then this is theta 2. Then you should consider this right triangle. Okay? So this is M2G cosine theta 2. Right? So it's a bit complicated. We will say that a bit complicated, but do we miss anything? After all these things, do we miss anything? Tension, right? It means tension. Now I have explained to you that tension should be the same in magnitude because it's massless. Well, we assume massless cord, so tension should be here of the same magnitude. Right? So do you agree? Okay. So I think you need to agree because if you want to solve this problem, yeah. But anyway, so now let's write down the equations. So here, for M1, let's write down the equation. Okay? So for M1, let's assume acceleration is here, and that's your x. So that's M1G sine theta 1 minus tension, right? M1G sine theta 1 minus the tension T equals M1 times the acceleration. That's the first equation. But for M1, there's another equation, which is the vertical direction. N1 minus M1G cosine theta 1 equals 0, right? Because that object has no tendency to move in this direction. So that's for M1. For M2, we also have two equations. All right? For M2, we have, now we assume this to be up. So be careful, okay? We assume the acceleration to be up here. So tension will be a positive quantity here. So tension minus M2G sine theta 2, and that will give you M2 times the acceleration. Okay? And now the last equation we can write down is the vertical component for here. So that's N2 minus M2G cosine theta 2 equals 0. Okay? So now let's look at these two equations, 1 and 2. How would you get acceleration? Try to get the sum. Okay? If you get the sum of 1 and 2, you will see that tension will get cancel out each other because the tension are of the same magnitude. So you have this thing, m1g sine theta 1 minus m2g sine theta 2. This thing will give you m1 plus m2 times a. And what is a? A now you will see a will become this, m1 sine theta 1 minus m2 sine theta 2 divided by m1 plus m2, this ratio times g. That's it. So again, this a will be less than g, because if you consider the ratio of a to g, you will see that it's less than 1. Now you can consider m1 times sine theta 1 minus m2 times sine theta 2. This quantity here, numerator here, if it's a positive quantity, that means our assumption was right. But if this is a negative quantity, that means our assumption was wrong. Okay? But if the assumption is wrong, that just means that direction of acceleration is into the opposite direction. Okay? That's it. So that's the key. Okay? m1 sine theta 1 minus m2 sine theta 2, that factor is to determine what's the direction of acceleration. Okay? So that's it. So thank you. Hope you will have a great day. See you again next time. Okay?